So last time we studied pole placement method using by designing a state feedback controller for a system. Right? In a state feedback control system, what we do is instead of feeding just the output of the system, we feed all the states of the system uh, back into the system via feedback gain controller K, and by properly designing the value of K, we can improve the performance of the system by placing the poles at any desired locations or by changing different performance characteristics of the system. Continuing with this, let's do another example. Say, for example, we have the system. System, you have been given a system whose state space model has been given to you. State space, state variable representation of the plant is x dot equal to minus 6 minus 4 4 2 times x plus 4 minus 7 times u, and y is equal to 1 minus 1 times x. Okay, so this is your system. Find the damping ratio of the system. And secondly, design a state feedback control controller which results in damping ratio of 0.7. Fine. So you have been given a system, you have been asked to find the damping ratio of the system, and you have also been designed to then design a state feedback controller for the system for which the damping ratio of the plant will become 0.7. Fine. So the characteristic equation of the system is given by determinant of Si minus A equal to 0, which implies determinant of S 0 0 S minus A minus 6 minus 4 4 2, determinant of this equal to 0, which implies determinant of S plus 6 minus 4 plus 4 S minus 2 equal to 0, which gives us S plus 6 S minus 2 plus 16 equal to 0, which implies S square plus 4S minus 12 plus 16 means plus 4 equal to 0. So we have this system S square plus 4S plus 4 equal to 0. Therefore, omega n, we know when compared with the general second order system, S square plus 2 zeta omega ns plus omega n square equal to 0, you have omega n square equal to 4, which implies omega n is equal to plus minus root 4, that is actually omega equal to 2 radians per second. Frequency cannot be negative, and 2 zeta omega n is also equal to 4. This term is equal to 2 zeta omega n, that means it is equal to 4, where omega n is 2. Substituting this, zeta will come out to be 1. Right? So your damping ratio of the original system is 1. Now you have been asked to design a controller for which the damping ratio will be 0.7. So therefore the desired characteristic equation in the pole placement method, we would get the desired characteristic equation by using this S minus lambda 1 into S minus lambda 2 equal to 0. Fine. This was for if we had to design the poles of this system to place them at a particular location. But But in this case, the desired characteristic equation will be s square plus 2 zeta omega n s plus omega n square. Fine. Originally omega n is 2, so we'll keep it at 2, but zeta was originally 1, but we have to get shifted to 0.7. We have been told to design a system for which zeta is 0.7 and omega n is 2. Therefore, this equation becomes s square plus 2 zeta omega n, that's 2 into 0.7 into 2, 4 into 0.7, that's 2.8 s plus 4 equal to 0. Now this is your desired characteristic equation and characteristic equation of the state feedback controller, state feedback control system. It is Si minus A plus Bk equal to 0, where you have Si minus A is S plus 6 minus 4, 4 S minus 2 plus Bk, B SI minus A हमने ऑलरेडी निकाला था यहाँ पे, SI minus A plus Bk, B is 4 and minus 7, 4 minus 7 into K, it's a row matrix K1, K2 equal to 0, which implies S plus 6 minus 4, 4 S minus 2 plus this becomes 4k1, 4k2 minus 7k1 minus 7k2. Determinant of this equal to 0, which implies S plus 6 plus 4k1 minus 4 plus 4k2 4 minus 7k1 S minus 2 minus 7k2 equal to 0. Cross multiply this, you will get S square plus 4 minus 7k2 plus 4k1 times S plus 4 minus 36k1 minus 58k2 equal to 0. Right? So you are getting this equation. This is your characteristic equation of the state feedback control system. This is your desired characteristic equation. Equation number 1. Equation number 2. Now comparing equation 1 and 2. You have 4 minus 7k2 plus 4k1. 7 minus 4k2 plus 4k1 is equal to 2.8. And you have 4 minus 36k1 minus 58k2. Equal to 4. Fine. So if you find out the value of k2 from here, k2 is minus 36 minus 36 by 58 times k1. K2 is minus 36 by 58 times k1. Substitute that here, you will get 7 minus 4 into minus 36 into 58 k1 plus 4 k1 is equal to 2.8, which implies k1 will be equal to 6.48 K1 is equal to 2.8 minus 7, that is equal to minus 4.2. So K1 will be equal to minus 4.2 divided by 6.48, which is minus 0.648. So I was putting this back here. Uh, K1 will be minus 0.648, whereas K2 will be 0.4022. So this is your. So this is one more example wherein we have to design the damping ratio of the system. We have to design the controller of the system so as the damping ratio of the system would be 0.7. For the original system, damping ratio was 1, but the desired damping ratio was 0.7. Fine. Doing another example, design state feedback controller for the following plant. The plant is x dot is equal to 0, 0, 1 minus 10 times x plus 0, 1 times u, y is equal to 1, 0 times x. So that uh, the closed loop system, that after designing the state feedback system, the closed loop system that we'll be obtaining has overshoot of 25% and a settling time of 0.115 seconds. So you have to design a controller K for this system, for which the peak overshoot will be 25% and the settling time will be 0.115 seconds. Peak overshoot here is MP percent is 25%, fine. So you can say it is 0.25, which implies you know the formula of peak overshoot of a system, e raised to minus pi zeta by beta, that's under root of 1 minus zeta square, is equal to 0.25. Applying ln on both sides, we'll be having pi zeta by under root of 1 minus zeta square is equal to 1.38. Solving for zeta, cross multiply and squaring both sides, zeta will come out to be 0.40. So for the original, for your desired system, zeta is 0.40. Also you have been told that ts should be equal to 0.115 seconds. That means 4 by zeta omega n should be equal to 0.115 seconds. Zeta is 0.40, therefore omega n is 4 divided by 0.4 into 0.115, which is equal to 86.29 radians per second. So your desired characteristic equation is s square plus 2 zeta omega n s plus omega n square equal to 0, which implies s square plus 2 into 0.40 into 86.29 s plus 86.29 square equal to 0, which implies s square plus 69.032 s plus 7445 is equal to 0. So this is your desired characteristic equation. Now your characteristic equation of the closed loop system is Si minus A plus Bk equal to 0. Your A is 0, 1, 0 minus 10. B is 0, 1. That means actually S minus 1 minus 0 S plus 10 plus 0, 1 times K1, K2. Determinant of this is equal to 0, which implies S minus 1 K1. This will be 0, 0, K1, K2. K1 S plus 10 plus K2 is equal to 0, which implies S square plus 10 plus K2 S plus K1 is equal to 0. This is your equation number 2. Equation number 1 is this. So comparing 1 and 2, compare 1 and 2, you will get K1 equal to 7445, K2 plus 10 is equal to 69.032, therefore K2 is equal to 59.032. Fine. So for this system we had to design a controller K for which the peak overshoot would have been 25% and settling time would have been 0.115 seconds something. So all you need to find out from those two parameters is zeta and omega n. Once you have zeta and omega n, your desired characteristic equation will be S square plus 2 zeta omega ns plus omega n square equal to 0. Compare it with the characteristic equation of the state feedback system. The characteristic equation of the state feedback system is determinant of Si minus A plus Bk put to 0. Fine. Okay, so this is your assignment. Assignment number 2. For the following system, x dot equal to 0, 1, minus 6, minus 5, x plus 0, 1 times u, y is equal to 1, 0 times x. Design state feedback controller that satisfies the following: A. Closed loop poles have a damping coefficient of that zeta is equal to 0.707, and also its step response peak time, that's peak time not peak overshoot, is 3.14 seconds. Fine. We have been given that zeta is 0.707 and TP is 3.14 seconds. So using these two values, you can find out the value of, you have already zeta equal to 0.707. From the formula of TP, you can get the value of omega n. So you can get the desired characteristic equation, compare it with the characteristic equation of the state feedback control system. You will get your values of K1 and K2.